Hi Year 12, this is part 4 of the videos on photoelectric effect. In this video we're going to look at the interpretation of the results of the photoelectric effect. So in the last video we saw that there are perhaps 4 kind of key results that we need to know about when you look at the photoelectric effect. The existence of a threshold frequency, so below a certain frequency you don't get any photo emission of electrons. The fact that the kinetic energy of the fastest electron depends linearly on the frequency of the light. So as you increase the frequency of the light above the threshold frequency, the kinetic energy of the electrons in general, but we're focusing on this value of the kinetic energy of the fastest electron increases. Thirdly, that for a fixed frequency of light, if we increase the intensity, we also increase the current of the electrons, so the rate of flow of the electrons from the surface. And finally, that when we turn the light on, the emission of electrons occurs immediately. So we're going to see in this video that the wave model of light cannot explain these observations. However, the photon model of light can explain those observations, and it was Einstein who used this photon model to explain the observations of the photoelectric effect. That was what he won his Nobel Prize for. Right, so we're going to start with the existence of a threshold frequency, and we can first of all think about the wave model. So let's just make a note. So we're trying to use both of these, the wave model and the photon model, and we're going to try and see if we can explain the existence of threshold frequency. So in the wave model, if you remember back to the first video, we said that if we think about light as an electromagnetic wave, the intensity of the light, the energy delivered by the light per unit area onto a surface per second, the intensity does not depend on the frequency of the wave. So the fact that we see different effects if we are changing the frequency, we can't explain that using the wave model. Fundamentally, what that light is doing is delivering energy to the electrons that allows them to escape from the metal. If we're thinking about light as a wave, then it shouldn't, changing the frequency should not affect the behavior of the electrons, because it shouldn't affect, or it doesn't affect, the energy being delivered to the surface. However, with the photon model, we can explain the existence of a threshold frequency. What we're saying is that now thinking about photons, we're saying that for a frequency below the threshold frequency, we have no emission. In our photon model, we're imagining all our photons coming down onto the surface, and we know that the energy of those photons is related to the frequency of the light. So below the threshold frequency, all we need to say is that these photons have an energy that is below the work function of the metal. Remember, the work function is the minimum, it's the energy required to free the most energetic electron. So if a photon doesn't have a work function worth of energy, then when those photons hit an electron, they're going to give the electron all of their energy. The electron is going to absorb that photon, it's going to absorb a packet of energy, but that energy is not going to be enough to free the electron, even if that electron is the most energetic electron in the metal. We should probably make a little sort of, there's an assumption going on here, which is a fairly sensible, is a sensible assumption. We're assuming that each electron absorbs only one photon. So in other words, we're saying it's very unlikely that two photons are going to hit an electron, be absorbed by an electron within, a certain small amount of time. Okay, so that's the first observation that can only be explained by the photon model. Second observation was the dependence of the fastest electron's kinetic energy, EK max. We said that that depends on the frequency of the light. Again, the wave model can't explain this because, as we said before, in the wave model of light, the energy being delivered by the light is not affected by the frequency of the light. So this observation just doesn't make sense under the wave model. Under the photon model, we can explain it, and this is where we're going to come across the equation, the formula rather, I should say, the formula that you need to be able to use regarding the photoelectric effect. So we're going to write down a relationship here using conservation of energy. The photon that is going to fall and be absorbed by an electron in the metal has a certain amount of energy. That amount of energy is going to be transferred to the electron, and it could be transferred to two different stores. It could increase the kinetic energy of that electron, and if the electron changes position subsequently within the metal or is freed from the metal, it's also going to gain, or at least change, the potential energy. So we'll write gain in potential energy because that's what's going to happen if the electron escapes from the metal. Okay. So if we go back and just revisit this diagram that we drew, I think in the second film, we were drawing this sort of scale with different energies of the electrons inside the metal, and we had this idea that there was a band, a range of different energies that our delocalized electrons could have. And there was a certain amount of energy that an electron that had just managed to escape from the metal would have. So if we kind of try and apply this idea onto this diagram, if we mark on perhaps an amount of energy that is our photon energy, okay, so we might have an electron that had this value of energy. It absorbs this photon energy, we'll call that HF. To escape from the metal, that electron needs to increase its potential energy from there up to there, and then the remainder of the energy that it's absorbed from the photon is going to be what it has as kinetic energy once it's escaped. Okay, so we've got potential energy and the kinetic energy. So that's just a graphic way of representing this equation. The electron that's escaped has increased its potential energy and its kinetic energy, and the sum of those two has to be equal to the photon energy. Now, if we think about specifically the most energetic electron, so now we're thinking about an electron that starts off here. If it gains that photon energy, HF, let's extend this a bit. The energy it needs to spend escaping from the metal is the work function. And the energy that it has once it's escaped, its kinetic energy, say, we've defined as EK max. So applying this idea of conservation of energy to our most energetic electron gives us this relationship. The energy that the photon gives is equal to the kinetic energy of that most energetic electron plus the work function, which is the amount of energy it has to spend to escape from the metal. So the way this is given in your formula books is, I think, rearranged like this. I'm just going to rearrange it. Might be wrong actually, I can't really remember. Okay, so we can rearrange that equation obviously in various ways. Last thing to do to just rewrite this slightly is that the work function, if we think back up here when we were talking about the if the photon energy was lower than the work function, we get no emission. If the photon energy is equal to the work function, then in that situation we are at the threshold frequency. So in other words, if the amount of energy our photon has is h times the threshold frequency, that photon has just enough energy to release an electron from the metal. And so we can write down this relationship, that the work function is equal to h times the threshold frequency. Okay, that's the amount of energy that a photon of light has when you are at the threshold frequency. So if we come back down here and substitute that in, we get that relationship there. Okay, I'm going to finish that video now so that it's not too long, and then I'm going to do another one to talk about the rest of the results.